Okay, so in this lecture, I wanted to briefly discuss some of the connections and differences between empirical Bayes approaches to shrinkage and penalized likelihood approaches to shrinkage. And so if you remember, well, one of the things I like about the Bayesian approach to shrinkage is it's kind of clear what the assumptions are. So if we, if we just, maybe go back to the simplest possible case where we have data xi, this is sometimes called the normal means model. It's kind of the simplest case where sigma squared is known, let's say. And then we have this prior on theta. So theta I, it comes from some distribution G, let's say, which in the empirical Bayes approach we would estimate from the data, and then estimate theta hat by say its posterior mean. Which depends on the prior, for example. The nice thing about this is we know it's optimal under certain conditions, in particular under the conditions that the thetas really are coming from that prior G, and under a loss function that, in this case, because we've used the posterior mean, it's a loss function that we squared loss. So we know that this kind of, assuming that the likelihood's right, the prior's right, and the loss is reflecting what we care about, then we know that this is optimal. So, for example, if if let's suppose we assume G to be a normal distribution, and I could ask myself, well, is that a reasonable assumption that the thetas come from a normal distribution in the setting that I'm looking at? And I know that I expect this procedure to work well if the answer is yes, or more generally, if the setting matches my prior assumptions. So with the penalty term, it's a little bit less obvious, at least to me, under what settings is each penalty going to do well or not. So far, we've just noticed or noted that the L1 penalty tends to give sparser solutions. The L2 penalty gives less sparse solutions. So the intuition is that the L2 ought to be better in cases where there's less sparsity, and L1 might be better if there's more sparsity. And there's a question, well, could we say something about when they're optimal? Are there settings under which those procedures are optimal? And for L2, it turns out the answer to that is yes. It's not that hard to say what the optimal is, whereas under L1 it's harder. So that's that's kind of a question that we might ask. So so firstly, let's see how there's a kind of a trivial connection here. So let's have a look at that trivial connection between the penalized approach and the empirical Bayes approach, or the Bayesian approach. So basically, the simple observation is that a penalized likelihood, maximizing a penalized likelihood or a penalized log likelihood, is equivalent to finding the posterior mode. So for example here, I don't know why it's the LaTeX not rendering properly here, but maybe I can, don't know if I can fix it. There we go. No, doesn't like that. Okay, so it's just an algebraic fact that if you multiply the likelihood times the prior and take the log, you get the log likelihood plus the log prior. And if you find the maximum of that and interpret the log prior as a penalty term, then you can say that the posterior mode is solving a penalized likelihood problem. Okay, so if you think about things that way, you can say that using if you do the math, we put in a p of theta that's normal here, we get an L2 penalty, because the normal is e to the minus theta squared, and take the log of that and you get a theta squared like penalty term. And if you put a double exponential prior in, also called a Laplace prior, that's e to the minus theta, absolute value of theta, e to the minus theta, that's the double exponential prior. Take the log of that, you get the absolute value of theta, up to a constant of multiple. And so log of P of theta, if you use a double exponential prior, is an L1 penalty. So this says that you can interpret the L2 penalty approach as finding the posterior mode under a normal prior, and you can interpret the L1 penalty approach as finding the posterior mode under a double exponential or Laplace prior. So that makes them look kind of like a Bayesian procedure, right? But you have to be a little bit careful. Okay, why do you have to be careful? Okay. Well, the reason you have to be careful here is here, that actually the posterior mode isn't really a very Bayesian thing to compute, right? So if you remember the posterior mode, well, particularly, I should say, particularly for continuous parameters, which is what we're looking at in these regression problems. So for discrete parameters, sure, a posterior mode is a fine thing to compute. But if you've got a continuous parameter, the posterior mode doesn't really make that much sense. And if you remember that the reason for that is, if you remember, the posterior mode is the optimal estimate under 0-1 loss. 0-1 loss is where you lose 1 if you get it wrong and 0 if you get it right. So it doesn't matter how wrong you get it. If you get it wrong, you just lose 1, however wrong you get it. And for a continuous parameter, you're never going to get exactly right. So you're always going to lose 1, whatever you do, essentially. And so, although in some limit the posterior mode is optimal, it's kind of, you know, optimal for a problem which is impossible to solve. And so this loss function doesn't make much sense in that case. So the fact that you can interpret these penalized likelihood methods as finding the posterior mode, and I should maybe mention the posterior mode is also called the MAP estimate. So MAP, maximum a posteriori. The MAP estimate, or the posterior mode, the fact that you can interpret them this way doesn't really give them a very, you know, it doesn't really help tell you what assumptions they'd be optimal under, or it tells you assumptions that are not very helpful. They'd be optimal under a 0-1 loss, which you don't ever essentially care about for continuous parameters. So although it's true that the penalized likelihood methods are posterior modes, that doesn't really say much about their optimality from a Bayesian perspective, except for L2 loss, it turns out that the posterior mode and the posterior mean are the same. So that's this. For if you use a normal prior and a normal likelihood, I should say, then the posterior is normal. And that's true also if it's a multivariate problem. So if you've got a multivariate parameter, as in a linear regression, the B regression coefficients are multivariate. If you put a multivariate normal prior on the B and you use a likelihood that's normal, as in a linear regression with normal errors, then the posterior is also normal, it turns out, on multivariate normal. And for the normal distribution, the mean and the mode and the median are all the same. So finding the posterior mode is actually also finding the posterior mean. So that means that for the L2 penalty, sometimes called ridge regression in the regression context, the L2 penalty, it's the same as the Bayesian posterior mean, specifically with independent normal priors on the regression coefficients. And it's the same as the posterior mode, but the posterior mean, let's focus on that. So that means that ridge regression will be, in some sense, optimal under L2 loss under a prior on the regression coefficients that they're coming from a normal distribution. So this kind of tells you that the kind of in a sense, you can see what the underlying assumptions of ridge regression are, and you can see when it's going to do well. So for example, if you simulated data by simulating regression where the regression coefficients came from a normal distribution like this, then you would expect ridge regression to perform very well. Whereas if they came from some other distribution, not necessarily. The same's not true for, you can't say the same thing for L1. You know, the L1 is the posterior mode under a Laplace prior, but it's not the posterior mean. So it's not really clear that even if you simulated data under a Laplace prior, for example, the lasso might not do very well, in fact, because under L2 loss anyway, or even under absolute loss, sorry, not L2 loss, under squared loss. Let's say. Okay, so what we take home is that ridge regression works well if the coefficients are normally distributed, could be less well if the true coefficients are sparse. Another point that this comes is that means you can think about ridge regression. You could imagine estimating the tuning parameter. We've looked at doing it by cross-validation, but you could also do it by empirical Bayes, and actually that's outlined in this write-up here. So you can take a look at that to see, you know, they're not exactly the same, but they're going to give you a similar estimate. And you could ask what method is better. Actually, I suspect that if the model's right, then the empirical Bayes approach will tend to provide slightly better estimates for lambda. But if the model's wrong, one could worry about that. So that's actually a question I don't exactly know the answer to, but we have seen, in simulations, we've seen some advantages of the empirical Bayes approach to choosing lambda, but those simulations were all done under the correct model, and you could speculate that maybe cross-validation would be more robust to modeling errors. So there's an open question for you. So, and that's all I wanted to say.